Zhang, who just came over from on the bus from Ithaca. So like, bear with him if he's still like sort of waking up a little bit. um, as I said, like I would like these conversations to continue. This is not like the end of the presentation in a way. Let's talk over lunch. Let's talk over time. Thank you so much for being here, and hand it over to Cheng now.
All right, good. Let me see what's the best way. Okay, maybe this is better. Hey, I'm Cheng, associate professor in information science. So today we'll talk about my lab's research on comprehending human behaviors with everyday wearables. So I'll focus on the application we have done on accessibility on the second half of my talk. So right now you give a talk, think everyone talk about AI on research, but AI have been great understanding everything, understanding your text, speech, images. But one thing, if you think about why AI becomes so good understanding text, images, speech, it's actually happening in past decade. But why? It's not because new algorithm, neural networks have been invented decades ago. It's actually because of data, because there are huge amount of data that was able to be captured, be stored, and be transmitted in much lower cost. So that's why AI can understand your text, speech, images. But if you think about, there's one thing AI cannot understand well at this moment, is actually us. AI, can have very limited understanding human behavior, your intentions, right? Think about the daily task, how human can understand us. AI cannot understand your daily activities, like your eating, drinking, that very basic activity AI cannot understand. AI can also hard to understand your health condition, like a test mentioned, because there's no way AI can track your symptoms every day. So that you a lot of time you overlook your symptoms, right? AI can now help you with that at this moment. And for accessibility, like people using, for example, a lot of people using American Sign Language as a native language to communicate, but at this moment, AI cannot understand them in daily setting to help them to communicate with people who are non-signers. So because AI have such a limitation on understanding human behavior, so these key applications have been limited. But why? Why AI have such a challenge to understand humans, similarly as why AI can understand text, image, speech? Because there's a lag. Sorry. There's a lack of high quality human behavior data in the world because there's no such data. That's why AI is so hard to understand us. Today I will talk one type of human behavior data, such as fine-grained body postures. What do I mean by fine-grained body postures? Fine-grained body posture here, I mean everything on your body that moves, including your facial expressions, your eyes, your gaze, tongue, neck, arms, fingers, legs, basically everything on your body that moves that I consider as fine-grained body postures. But why they're important? Because we use this complex body posture to interact with computers. Well, use your mouse and use your hands to input on the keyboard and mouse. That's one part, but more importantly, we use body posture to interact with the physical world. Right now, everyone's using body posture to eat, to drink, to grab a pen. We're also using our body posture to communicate with each other. So right now, I'm using my body language to communicate how excited I'm giving a talk. Use your facial expression to communicate with me and telling me how much you like my talk as well. So what I'm trying to say is body posture is actually key of human interact with the entire physical world. So therefore, collecting high quality fine-grained body posture is actually in everyday activity fundamental for AI to understand human behaviors. So my task is, can we enable everyday wearables to track and understand human behaviors from body postures? So here I highlight everyday wearables. That means I don't want to invent wearables that are cumbersome, change your behavior, change your appearance, and no one gonna wear. I want the wearable that you already wear, like your watch, your glass, without changing their appearance. Can we make them smarter? So in order to science tracking those fine-grained body posture in the wild is super challenging actually, because first it has to be minimum obtrusive, otherwise no one gonna wear them in every settings. It has to be low power. If it kill your power, in 10 minutes, no one gonna wear that. The third part also you need to consider privacy. Privacy is a big part. About 10 years ago, I actually wear Google Glass for almost 1 year every day. You know what question I got asked most frequently, almost every day, is once people see I'm wearing Google Glass, people ask me, "Are you recording me?" Right now it's still the thing. Imagine go to a meeting with someone wear smart glass with camera, you'll be concerned. So when you design a system on wearable that understand human in every setting, so privacy is thing you have to consider when you design a system. Well, satisfy those requirement, the most important thing, or one of the most important thing is the system has to be capable of capture high quality behavior data, right? So that's a goal. So what my research does is, first step, we're building a wearable platform that can track all kind of body postures. And then based on the high quality body posture data, then we'll show, based on the data, we can allow AI to understand human behavior that it can never done before. I will demonstrate accessibility application today as well. So this is the two part of my talk. The first part, I'll talk about how we're using ecocentric active acoustic sensing on wearables to track body postures. And then we'll show how once you can track all kinds of body postures, how you can use them to understand human behaviors, especially on accessibility applications. So I'll start with the first part. So this is a key part of my the research we have been working on the past couple of years. We call ecocentric active acoustic sensing. What it does is that we put speaker and microphone on a single wearable. The speaker will generate inaudible acoustic wave. Imagine ultrasound that will cover your body. Imagine wherever you are, you have acoustic aura cover your body. And then when your body move different position, you're holding different object, you will reflect acoustic waves with unique patterns captured by the microphone same device. Then by analyzing the reflection of acoustic waves surrounding your body, you can understand everything you do, from your face to your foot, from what object you're interacting with. So that's the thing we're doing. And give you talk a little bit more about this part. I won't talk too much detail, but give you a little bit of technical detail how it works. So imagine this is example of smart glass. So we're sending this kind of encoded wave downwards from the speaker is on the hinge, pointing downwards, and then what happened is your body will reflect acoustic wave a unique pattern. Then we actually do some math calculation, and here cross correlation. We'll do the calculation. Well, calculate something called echo frame. Echo frame means that at this moment we're scanning the surrounding object. At this moment, where are the things nearby you? So at that moment. So and then if you stack the scanning at time domain, and you will call the echo frame. In echo frame, basically, is a time series analysis of what are the objects surrounding you, including your body, own body. So give you some highlights how to understand echo profile here. So this is the picture, actually data captured from a glass. Y-axis, you see the number, that unit is centimeter, represent where are the object are in terms of one-way travel distance. Okay, so that's y-axis, x-axis is time. So imagine the zero distance, that's where the sensor are on glass. But if you look at the reflecting distance, this actually map your body. If you look at a reflection under 15 centimeter, that cover reflection on your face. If you look at lower, the upper body, and even long distance is the lower body. So by just simply looking at the reflection distance, you can understand the information on different part of body with one single sensor. And then we can actually, I'll skip this part, and then we can put the data into neural networks, and we can estimate different kind of body postures. So the question, of course, is what kind of body posture you can track? The answer is all kind of body postures. We'll start with something simple, which are called coarse body movements, which is upper body pose. Because upper body pose, you have your arms, which huge object will reflect, will have cause reflection. So it's easy to do. The first work we actually turn. You can see that that's a speaker microphone. We can enable your smart glass using the acoustic wave to track your upper body pose, right? So that's, you can see the demo here. So that's our first kind of work on this line. But that seems very straightforward and easy because your arm is so large. It won't be surprised you can capture that. But can we actually capture more subtle things? The answer is yes, because acoustic sensing has millimeter level resolution. So it's really high resolution. So looking at this reflection, So the first work, we actually look at reflection in this range, in this reflection range. But if you look at reflection under 15 centimeter, what it cover your face, what you can learn from the reflection under this short range. So that's the work we did. We can track your facial expression, track your gaze from this part. The first work is this. You can see this is the earphone speaker microphone on the here. You're shooting acoustic wave just by modeling the skin deformation on this area. You can see that that's a signal. And we can estimate entire facial expression just using acoustic wave to modeling the fish skin deformation on the cheeks, right? So that works very well when you're walking, but it has a limitation. The limitation is that um, it doesn't track well when you do blinking. If you close your eye, open your eye, it works. But blinking is so subtle, so the skin deformation here does not reflect well. The second limitation is that it requires a lot of training data. So we go on work on the second part, which is the smart glass. The smart glass, with this one, you can see we can even track the blinking very well. You can notice the blinking, and the system is real time and deployed on the phone. But just using acoustic waves on this part. So the second work, we actually can track everything and have better performance and reduce the training data by a lot. We can track your blinking, but the question, can we do more? And that's our Mobicon paper last year. We can even track your gaze from this part, from acoustic waves. How does it work is that your eyeball is now round shape. So when your eye is looking at different direction, the shape in this area is different. So you can using acoustic wave to modeling the shape of this area, and then you can track your gaze. So the blue color is our tracking. The red color is actually ground truth using camera-based system. Um, okay, so that's a part. So far, I have shown a lot of work that actually on the glass on mostly cover your head, but we can actually do more like more complex body poses here. So then we move to other form factor are more popular like a wristband, and a ring. In this case, the first work here is actually we can turn your wristband to track not only your hand posture but also what object you're holding because we can send in acoustic wave. I can see acoustic wave here. That's a speaker microphone. The acoustic wave will be reflected by your hand pose and object in your hands. By doing that, so we can actually understand your hand pose continuously and also what object in your hands. That's a estimation of a hand pose. In next part show, yeah, we can know what object in your hands because we're modeling the shape of the object in your hands as well. Not only that, if you put the speaker microphone on a single ring, and this ring can also track your hand pose continuously as well, because it's like more like sonar, keep scanning where things are nearby the finger. Right. Okay, that's enough demos. But that's the first part. I talk about so how we can using this simple acoustic sensing to track, from your face, gaze to your full body postures. If you look at reflection, the requirement of tracking body posture in the wild, this system are pretty small. You can make it as small as your normal device. So won't change your appearance. It's relatively low power, and compared to camera, this system, because ultrasound is much more privacy friendly. And more importantly, those speaker and microphone are already existed in your existing smartwatches, and our smart glasses. So they have potential to be deployed immediately on those devices. Okay, now I'll go to the next part. If you can track those detailed body posture in every setting, how can you help AI to understand human behavior and intention, especially on accessibility? Okay, so we have a lot of application we have done, but I want to focus on accessibility application today. So there are two accessibility application I want to do. One I call silent speech interface. Second one is American Sign Language translation. The first part is silent speech interface. Silent speech interface. What is silent speech interface? Is understand your speech without using voice. And the question is, why do I need that, right? Why do I need silent speech interface? Because first, sometimes if you talk to speech interface, you have to speak out loud. And that can leak your privacy, can also be socially awkward right now. If I talk to my watch, it will be socially awkward. But more importantly, there are a lot of people with speech impairments actually. The speech people with speech impairments, they cannot using speech interface. They cannot even using speech as daily communication tool. So it's important to understand people's speech intention without using voice. So from this line, we actually start first work, which is on Kai, that we're building a smart glass and also using acoustic waves. So we're sending acoustic wave by modeling the shape and skin deformation around the mouth, this area using acoustic waves. We can understand your speech continuously with under 5% word error rate on selected dictionary. So this way it is the first of its kind that can do continuous speech recognition with high performance. With this system, you can see like now you can actually use them for like if you do CAD design, you can silently name the parameters instead of using a soft keyboard to typing. This work is great, but this work one limitation is they require customized hardware, right? So even a small micro speaker, they need new hardware. So can we enable the silent speech interface on off-the-shelf wearable? The answer is yes, because many of us have noise canceling headphone. Noise canceling headphone already have speaker microphone. We can turn them into a sensor to understand your speech without adding new hardware. So we're using turn-based Bose headphone, and we're actually using the speaker to generate inaudible sound mixed with the music you're playing, and using the microphone capture reflection. By this way, we can actually understand what you're trying to say without just using off-the-shelf watch by modeling the movement on this point. I don't want to show you one thing. This is a recognition, but the signal is on blue color one. You can see when you're moving mouse how clear the signal are, how distinguished your pattern are on the acoustic sonar reflection. This is cool. But what really motivated us is after those two works, we have even last week I got a message from people, from patients who lose their voice, have vocal cancer. They actually reach out to us saying, this is the only hope you have. We want to use your system. There are people from Connecticut say where we can drive to Ithaca help. You know, Ithaca is in the middle of nowhere. They're willing to drive there to help us test the system. We're really motivated by that in the past couple of years. As a result, one of my PhD students decided to pursue this direction as his PhD thesis. Actually, I will show the work. Because the question we have is, okay, now the silent speech interface is really cool, but what really matters is, can we give their voice back? For people who lose their voice, can we really give the voice back? That's our latest work under review. You're the first group of people who have seen the results. So this work would really give people's voice back. We actually did a study with collaborate with Cornell Medicine. We actually did a study with laryngectomies. So who are laryngectomy? Laryngectomy actually are the people who have vocal cord cancer. This vocal cord, this part are completely removed, so they can now generate any voice. So there are several ways to treat them right now. So one way is actually you need a surgery to do things. Very expensive, that not work for everyone. The second way, let me see if I can play some noise or sound here. And this, yeah.
I'm from the Kansas City area.
So
I've
this is the second way, which is called the electrolarynx.
laryngectomy.
The electrolarynx is a device, handheld device you put here. You can get a monotone robotic voice, but clearly it's very different, have a lot of noise, doesn't work well. And the third way is actually a lot of researchers in the field trying to develop different wearables to recognize your voice, but those things cannot really continuously estimate your voice or give your voice back. So what we're trying to do is actually the goal is using AI to give the voice back. So we developed an AI-powered speech synthesis with intelligent wearables. So this wearable, including a neckband and a glass. So the idea is actually we're generating acoustic wave from the neck and vibrate this area, capture reflective wave on the glasses. So and then we can modeling the movement internally on the neck and your mouth. By doing that part, and for the sake of time, this is complex. We build like a GAN-based voice thing. I will show you the just results. So we actually did a study with 26 participants, including 11 laryngectomies. It's very hard to do them. Actually, we have to, my student have to go near city, go to big city to find a patient to study. And then I'll just go some samples. Okay, so the first sample is the sound from electrolarynx, the one you think. That's how you hear like.
You know what you have
Right.
to do.
So that's the current solution you hold here. And I will show the sound capture, original sound captured by our device. This is the raw sound captured by our device. Right. That's a sound. You can now tell what they people saying, right? And after denoying it a little bit, you can hear a little bit. But I will show what we were able to do with AI.
You do what you have to do.
That's what we actually generate from the second sound here. Sorry.
You
No.
know what you have to do.
This is sound we capture on your body. You cannot tell anything. And the final outcome is this one.
You do
Sorry.
what you have to do.
That's what we're doing. You generate AI to interpret the acoustic on the body to generate sound for them. So now they can really have the voice back, and they can choose what voice they want to be represented. They can use. We just need a few samples from the original voice. We can give their voice back to synthesize that part. Another amazing part is that this is we can even do without collecting it from the patients. So this is the data trained with data including
Can we get
oops.
can we get you a drink?
This is a model trained with both largectomy the patient and people who have who can make voice. But collecting data from largectomy trained model is very hard. So can we actually collect data trained with for normal people and deploy with them directly? So and then see the result. This is the result we trained with people without a largectomy patient data.
Can we get you a drink?
So sound is actually as good as the other one. So now we're actually continue working on this one, so we can collect large amount of data, help them to really have their voice back. So that's the first kind of work we talk about silent speech. The second part work I want to talk about is American Sign Language. Because we have developed a platform that can track your facial expression, your finger posture, and body posture. Because American Sign Language is actually very complex gesture. It's not only fingers, it's combination of fingers, arm, facial expression all together. So we started first work this year, Kai, is we actually turning a ring that can understand finger spelling of American Sign Language. Finger spelling is a small part of American Sign Language. So what is finger spelling? This is my leading student, Heng Chu. He actually does this work. He actually take American Sign Language course at Cornell. So finger spelling is where you spell your names, or they don't have signs to spell them one by letters, right? So HY. So just like we spell out everything single. So why it's so challenging to recommend American Sign Language? Because if you work with signers, every signer has their own behavior. So in this example here, you can see ASL learner, they sign things very each letter clearly distinguished from each other, and native signers sign much faster and they have much blurry ways of signing. So it's really hard to do it with native sign, but that's our goal. We want to design things that they can perform at the native way they perform. So that challenge, in order to do that, you have to track all finger postures. You have to allow people do not, because I don't want them to change their behavior. They should sign as a native way to sign. So don't change the speed, don't change the way of signing. So they have a very fast speed. So that's a ring. So we have a ring that can track the whole thing. Just with a single ring, we can track all your finger posture and sign continuously. So our contribution is actually we will start working with people from deaf and hard hearing community, design a study, evaluate them, and then we can allow them to do the natural behavior of finger spelling and build a real-time system. So this is a system. We have acoustic sensing, which can track hand postures continuously. And then in order to address the blurry transition, we design complex machine learning algorithm to do that part. I will just show you the final results. So we actually conduct study with 20 signers. In there are 13 of them are native signers. There are 7 of them ASL learners. So with them, we actually have a long study, 3 days study. And then we actually ask them to sign over 1,000 words. It's a lot of words. And then we are able to achieve over 82% accuracy. If you break down the performance, you realize this graph shows X is the speed of the performance, and then Y is the is actually accuracy. You see that what happened was if people sign too fast and our performance drops, and if your ASL signers, it's actually much better. So that's the thing we learned because each signer not only signs very fast, but also they have their own habits of signing different words. That's signs very complex. Beyond that, we actually, if you apply word prediction on this part, we can actually achieve under 10% phrase level accuracy. That's first work. But then American Sign Language actually, a lot of people, was not aware American Sign Language is actually beyond just fingers, arm. Facial expression is also critical. So that's the next work, which we're going to present in 2 weeks at CSW. In this work, we explore the importance of facial expression in ASL translation. Let me show you a video. This is the signer performing a signs. You can see their fingers, arm, and facial expression all together, right? So that's a sign. But the question is, what emotion do you see from this facial expression on this signer? You you can take a guess. What are the emotion you're trying to express? So there are seven possible answers, like happy, sad, angry, terrified, disgust, surprised, neutral. And the correct answer is actually neutral. So, and when we do a study, we have actually 26 participants watch this kind of video. What's the result looks like? That's a distribution. You can see major people, by just simply looking at facial expression, they can now understand the emotion the signer trying to communicate. That's the key, right? Why is that? Because facial expression in ASL is beyond used only for emotion. They also use for linguistic markers. So when you observe the actual combination for emotion expression and the linguistic marker together, so and that's why making it very hard. If you're a non-signer, you don't understand linguistic markers, so make them together will confuse you. So then as a result, when you see the translation result, you have a mismatch between what kind of emotion they're trying to communicate. So what our argument is, it's very important to understand ASL, not only for finger and arm, but also you need to including and understanding their facial expression, to including emotion into the translation. So our research question, first one is actually, how does non-signers understand facial expression? By just looking at that part, we show that it's very challenging for non-signer to understand emotion correctly just by observing the face. The second question is, if we integrate the emotion into ASL translation, whether that will help people to understand emotion better. So then that study, we actually have 7 emotions, 7 linguist markers, and do a study with surveys. And the 3 conditions. One is we just saw subtitle of translation results, no voice. Second, a neutral voice, no emotion involved. And third one, we have emotion into like generated voice. The result shows that just observe the subtitle and neutral voice, people, this accuracy on recognizing emotion, people have very low accuracy understanding the emotion. But if you are able to add emotion to that part, it significantly improve people's accuracy on understand the signer's emotion. Okay, so for time's sake of time, I'll skip this part. I want to just highlight that my lab's research actually building wearables to understand human interaction, human activity and intention. So we want to focus on 3 applications moving forward. One is health. Another second part, big part, accessibility. Because accessibility, one part is understand people's intention and understand people's needs. So that's what we really want to use AF for. Um, so yeah, sorry, let's slides. Yes. Overall, my lab developed minimum obtrusive wearables, which are low power and press aware, that can understand human behaviors. But when we understand human behavior in the wild, the goal is not track you, but the goal is to support humans on this go. Okay, so last slide. I cannot do this work without my amazing mentors and PhD students, master student, and we have a lot of undergrads in our labs to work with us on this. All right, thank you.
So we're going to go to a couple of questions, if anyone has any.
I thank you for the presentation. It was amazing, but I'm also just very curious, like how does this apply like in the real world where there's like ambient noise and like audio that might affect like the acoustic signals? Yeah, sorry, I'm not an acoustic expert, so I
Yeah.
just wanted to understand.
Yeah, yeah, that's fine.
Thanks.
So, because we only play with ultrasound range, so the most of the sound we're generating in real world are audible range, so they won't interfere with each other actually. So it's different frequency range. There are no conflict. When may have some overlap with that part, but most part is fine. We actually test the system outdoor as well. It's mostly it's fine. And another nice part is because we're all not interested in reflection in like a half meter, 1 meter range. So we don't care about things far away as well. So that's another reason why system it's it doesn't was not will not be impacted a lot by real world noise. Yeah.
If there's like multiple sensors, like if you're wearing multiple rings, also will that interfere with each other?
So if one person wear multiple ring, that can be, but then you can choose different frequency while different devices. They can do that part. With two-person, unless two-person really hug each other in this range, otherwise it won't work because it won't impact each other. Because you can imagine the acoustic wave is like like a circle around you. Only when the other person really get close to your circle, otherwise it won't matter.
I actually have a question. So are we making some assumptions here that everybody's body positions are communicating the same information and that a person's body positions don't communicate different information over time? So you have one type of communication with your body position when you're a child, and then when you're older like me, those same body positions are communicating, I'm cold, not that I'm ignoring you.
Yes. Yeah, great question. So yes, everyone's body language can communicate different meaning when at even at different setting, different age. So our goal is actually building a ChatGPT for behavior understanding. So in the future, they will understand you based on your age and background, intend to understand that part. But I agree. So body language it's important thing that it's changed so much depending on context. That's why I want to collect huge amount of data so that I can build a ChatGPT for behavior understanding so they can not naturally understand your behavior as they understand your text and speech right now.
All right, cool. Let's thank Cheng one more time for a great presentation. And I know that we're a little over time, like some of the talks we didn't want to interrupt, and we started a little later, of course, because of the whole bus situation. So we have for the final talk in this session,